DNA data storage. It's not science fiction anymore. We're going to talk about it today on Biotechonomics TV. So we're hearing more about DNA data storage. You might have seen in the news a few weeks ago, Microsoft, Twist Biosciences, Illumina, and Western Digital announced they're creating a consortium to promote the technology and to advance it in the marketplace. And you start thinking, well, why? What's going on? And really, a lot of what's driving this is simply the cost of reading and sequencing DNA has fallen so dramatically that it's now possible to use it for things that outside of traditional lab applications or therapeutics. And one of the things about DNA is that it's dense. And you think, why would typical electronics companies or disk drive manufacturers, why would they be interested in this? It's that density. If you think about it, the reason your storage tends to get cheaper every year is as time passes, they're able to put more bits per square inch on a typical disk. A few years ago, they topped 1 trillion bits per square inch. This is a constant struggle that the drive manufacturers are in, and typically what you see is an increase of about 20% per year in terms of the density, meaning how many bits they can put in a square inch, and at some point you run up against natural laws of physics and how much can be done there. DNA is so much more dense than a standard disk drive. Think about it. Think about your body, okay? Close to 100 trillion cells in your body, each of which has 3 billion base pairs of DNA. That works out to something like crazy amounts of zettabytes for now. Now, here's an interesting comparison. Now look at this vial here, this glass vial. This is where Netflix is storing backups of a single episode of its from its Biohacker series. They put 1 million copies of the episode in that one glass file. So if you do the math, it's roughly 2 gigs per minute of storage need for 4K video. Works out to maybe 5,100 petabytes just in that little glass file. If you were to do that in a standard data center with standard electronic components, you'd be picking up about 5,000 to 10,000 square feet of floor space in the data center, and you need about 1 megawatt of power for the electricity supply. So DNA offers a tremendous amount of density that you're just not going to get with standard electronics anytime soon. DNA is obviously also a lot more durable, which leads to the use of this technology, which is mostly for long-term backups and archiving. Because this is write-once technology, it's not going to replace your hard drive anytime soon. It's ideally suited for those types of applications. Now you just start thinking, well, wait a second, DNA, that looks like it's being stored in a liquid, my computer's electronic zeros and ones. Well, obviously there needs to be a way to bridge the world of the 4 bases of DNA, A, T, C, and G, to the zeros and ones that your computer can understand. And there's an encoding and decoding mechanism whereby you simply take each letter, A, T, C, and G, and it translates into a sequence, 2-bit sequence of 00, 10, 11, and 01. And that's really important for doing that logical move from bits that your computer can understand to the DNA storage medium. Now, this is the thing with the applications. I think as costs come down, I think there's probably going to be some more maybe unintended uses for this. Who knows what some of the applications might be. But one other key thing that needs to happen to advance this a little further is the cost of writing DNA needs to come down. So I talked earlier about how the cost of reading DNA has been coming down exponentially. The cost of writing it has really only been coming down linearly. So there's work being done to make it cheaper to write the DNA, which in turn will help reduce the cost for what we're seeing right now, which at this point we're still talking early applications. It's scientifically possible, works well technically, but the economics aren't quite there yet. And in order for them to get there, that's going to be a key part of it. So where does this go in the future? We'll really have to see, like I said, I think we'll see some unintended applications. And I do think as time goes on, we'll start to see more backup archiving, especially areas where you need to hold data for years and years and years. You need much more durable DNA instead of electronics that are basically built to last really typically just a few years. But we'll see. I think it's an exciting technology and one that really is worth paying attention to. That's it for today. Thanks for joining. Please subscribe, and we'll talk to you next time.